Hi everyone, today Shuvan, Xingyu, and me are going to share with you a paper called Dynamic Right Sizing for Power Proportional Data Centers. So let's get started. The motivation of this work is to solve a prevalent problem in modern data centers, that is the energy consumption. The authors of this paper argue that the electricity bill of a typical data center with 50,000 servers usually costs around $1 million for every month. So I borrowed the data from our third lecture, and we can see here for these well-known data centers like AWS, Microsoft, and Google, their electricity bill is enormous, not to mention other bills. Therefore, to build an eco-friendly system and also save some extra expenses on the data centers, the authors of this work proposed the solution called dynamic right sizing. The idea is relatively straightforward. Basically, we just turn off all the unused servers when we are in a low demand time. And when there are more requests coming in, we just wake up them again and process all of them. So if we take an analogy to running a coffee shop, we can imagine ourselves as a coffee shop owner. Then during the lunchtime, when we have a lot of customers, we want to hire as many staffs as possible to process all of them. However, during the break times, as a coffee shop owner, if we still hire the same amount of staffs, then we will have a big headache of paying all of them in full. Although the idea of dynamic right sizing is relatively simple, the implementation is non-trivial for the following reasons. First of all, we have to come up with a method to seamlessly turn on and off all the servers without losing their states or data, because we know that all the requests and data are distributed among servers. Secondly, the administrators will usually worry about the wear and tear consequences. That is to say, we all know that turning the machines on and off frequently does no good to that lifespan of the machine. Thirdly, and also most importantly, we are unclear about how many number of servers we have to turn off during the non-rush hours. This is because we have no prior knowledge about the future, i.e. how many requests are coming for the next time. There are some previous works that also work on the dynamic right sizing. The authors mainly categorize these works into two streams. The first one that working on the analytical part, which develop algorithms with provable guarantees. However, the authors argue that these work usually fail at the worst case guarantees. Second part will focus on implementing system with substantial savings, so there are more practical works. However, these works are mostly specialized on certain frameworks, and they also ignore the switching cost, which is an important main concept proposed by the authors. Therefore, here we did a quick summary of the contributions of this paper. First of all, it proposes a general mathematical model that will be more generalizable compared with the previous analytical work we just mentioned. Secondly, they came up with a complete characterization of the optimal offline solutions. That is to say, we will have a good benchmark of comparing our work to the theoretical optimal. Thirdly, and most importantly, they introduced a new online algorithm called lazy capacity provisioning and validated their solution with significant energy cost savings. So under some certain contexts, the energy saving will be ranged from 15% to 30%, which is a big amount. So to begin with, and also reveal the mystery of their amazing work, I will introduce you the model formulation, which is comprised of many two parts. The first one is called operating cost, and the second one is switching cost. And we will go through them one by one. The operating cost is defined as the cost due to the delay from using fewer servers, and also the energy cost for maintaining one active server with particular load. Going back to our previous coffee shop analogy, we can imagine these as the cost we have to pay for potential revenue lost for being understaffed during the rush hours. And the second part, we can imagine that as the potential pay the staff will request for being overwhelmed during those rush hours. And the switching cost is defined as the cost incurred from toggling the server into and out of the power saving mode frequently. So in this case, we can imagine that in our coffee shop example, we have to, if we have to switch the staffs between shifts frequently, not only the staff will be unhappy, the customer will be unhappy as well because all the ongoing works need to be transited frequently. And here is a mathematical objective function definition of the model. So we can see on the left-hand side of the plus sign, it's the operating cost, and on the right-hand side, it's the switching cost. So we can see here we take a summation over the t, which stands for time. That's because this model will discretize the time of interest of the operating data center into certain amount of time slots. So assuming that we have 3 time slots, then the xt will stand for the number of active servers for each time slot. And the gt is the convex function that approximates the operating cost of xt servers. So assuming that suppose that we have 5 servers active during time slot t1, then gt of xt at t equals to 1 will be gt of 5, which is the operating cost of that 5 servers. And on the right-hand side, it's a similar summation, but this time we are summing the switching cost at different or at individual time slots. The xt minus 1 is basically the difference in the number of active time slots between 2 neighboring time slots. And the beta parameter here is the parameter that defining all the miscellaneous switching cost. As we mentioned previously, the switching costs have several components: the tear and wear cost, the turning on and off cost, and also the cost for opposing every work into an individual server. So it is the one parameter that defining all the costs that can be incorporated in switching cost. So in short, this equation basically defines the total cost of a data center under discretized times, and what we want to do is to minimize it. Actually, there are some problems with this model formulation, and that's what I want to do before I transition to the next presenter, is to share with you guys some of my personal comments. First of all, I'm very interested in this time discretization method because in the section of related work, the authors mentioned that there are some other event-driven models which care about the discretization based on the requests or the servers instead of the time. But they didn't really argue why they chose the time discretization over the event-driven models. Secondly, which is also one point that confuses me, is that the key observation that motivates this work is that the authors believe that the workload of data center varies from time to time. Therefore, in their work, they naively average the full time by the number of time slots, which means that it's just a linear discretization. However, in a varying system, we will have bad discontinuity using linear discretization. So I'm wondering why don't they choose a multi-resolution time discretization? Unfortunately, these questions are left unanswered in their discussion. Thirdly, is that this optimization problem is easy to solve in an offline setting, which means that we have all knowledge of all the time slots. However, realistically, this is impossible. This is impossible because we are not playing the role of God of knowing the future. With some unknown future, the optimization problem need to be solved cleverly using some online algorithms, and that's where the Shubham will going to discuss everything in more details.
Hello, I'm Shubham Chaudhary, and I'm going to be talking about receding horizon control. So basically, future time slots with predictive workloads are generated by forecasting models like time series and LSTMs. And then our CH picks a window consisting of multiple future time slots, and over that window, it is optimizes to find the best decision. Um, Basically, it implements only the first decision from the solution and discards the rest, and then shifts the window forward and then repeats the process again. So you can think of this like running a coffee shop where you check foot traffic forecasts for 30 minutes and then adjust your barista schedule for the whole window. But then you only follow through on the first few minutes of the plan and then redo everything from scratch in the next cycle. So basically, with that analogy, as you can see on the left, like the this is the equation for RHC, and the first half is the operating cost over the window. It's a convex function, and it's similar to making people wait in line or paying idle baristas. The right half is switching cost terms. So basically, if you're adding servers or removing servers, and yeah, the constraint is you can't have negative servers because you cannot have no baristas. So yeah. And then what's the catch? RHC works well, but it's very sensitive. If your forecast is just a little off, the cost can spike significantly. Also, the performance depends heavily on how big your prediction window is and what your switching costs look like. It's like trying to reschedule your baristas every hour based on shaky customer predictions. You either end up short-staffed or waste money overstaffing, and both can hurt. Tuning it well is tough in real systems with the noise, delays, and constraints involved. So now we're going to talk about optimal offline solution where it's the theoretical best case strategy for minimizing the total cost. This solution is used as a benchmark to compare against other online um, algorithms. And basically, it has a complete knowledge of the future, which means we give the algorithm the entire trace at once. And then since it has the entire knowledge of the future, it minimizes the cost over the entire horizon or trace. Um, and then basically, it builds the perfect solution backwards in time, starting at the end and working towards the beginning, and ensuring minimal toggling and minimal operating costs. And then basically, think of this like replaying a full day at your cafe with the perfect hindsight, and then designing the barista schedule that would have cost you the least. Obviously, we can't do this in real life, but it helps to see how close our algorithm comes to the ideal. So the upper bound is the optimal solution if only adding servers is costly, and the upper bound is the optimal solution if only removing servers is costly. And the perfect optimal solution is always between these two bounds. And basically, it calculates it in backwards in time, so it already knows the ideal. It already has the global picture, and it does not constantly fluctuate. It's lazy. It only fluctuates if like it's required, if the optimal solution crosses the boundary. Then we're going to talk about the main focus of our entire paper, which is the lazy capacity provisioning, which is an online algorithm, which means it does not have the entire data or time series with it. The online algorithm is designed to make near optimal server allocation, but without knowing the future. But it's inspired by the lazy behavior. But it also works in real time using only limited or even zero look ahead. So basically, it does not need to have like the future data or future predictions. It even if there's no future predictions or a very few future prediction, mainly uses the past data or the history to make decisions on whether to increase or decrease the number of servers. It also maintains the lower bounds and upper bounds similarly to the offline algorithm, and it. It's very robust, and since it cannot get thrown off by bad forecasting, since it can operate without any forecasts or minimal amount of forecasts, and it's three competitive, which means at most it's three times the cost of the optimal offline solution. At each time step, it calculates a safe lower and upper bound for many servers, for how many servers need to be active. If the current number of servers is already within that range, LCP does nothing. If it's outside the bound, LCP adjusts just enough to get it back inside. No overreaction, no over planning. So basically, LCP is like checking every hour whether your barista count is too high or too low. If it's fine, don't change anything. If it's too low, you should bring one in. Um, if it's too low, you should bring someone in, and if it's too high, just send someone home. That's it. And you're not making these predictions based on, sorry, you're not making these changes based on uh, predictions ahead of time. You're mostly using predictions right before the real time. And so basically, as you can see, this is LCP versus the offline. So in the offline, which is on the top, the bounds are more like sharper because it has the holistic view. So it's making the optimized best changes required. Whereas LCP is making it's performing pretty well, and but it's making those changes in a more subtle and more continuous manner. Especially if you focus on time T 5 hours. Near 5 hours, you'll see on the top there's a sharp turn, whereas on the bottom it's a gradual turn. Yep, that's all for me. Thank you.
I'll walk you through the case study evaluation of this lazy capacity provisioning, which is LCP algorithm. Our main goal is to test the cost-saving effectiveness of LCP using real-world data. We will compare LCP with a static provisioning strategy, which using a fixed number of servers, assuming perfect knowledge of future workloads. Imagine we have a coffee shop. A static strategy is like having a same number of staff all day, regardless of the demand. Other strategy might adjust constantly, reacting to every change. But LCP is smarter. It shifts resources slowly and only when needed, which saves cost while maintaining performance. We define the total cost as the operating cost plus switching cost, where the operating cost is the energy cost and the user delay, and switching refers to turning the servers on or off. Switching cost is something unique in our LCP model. We will use two real-world workload traces. The first one is Hotmail, which record 40-hour periods. This is a stable, smooth load. Even at night, there is activity like backups and indexing. The second one is MSR Cambridge, which lasts about 1 week. This is a more fluctuating load with much lower usage during the nighttime. These two examples will help us to see how the LCP performs under different load patterns. We will first study the impact of prediction window size. Intuitively, larger windows means better forecasts and planning, leading to greater cost reduction. When the window size is small, LCP becomes better over RAC methods significantly. Next, we look at the effect of switching costs, the cost of turning servers on or off. On the x-axis, we vary the ratio of switching cost to operating cost. It means how much operating cost is compared with this amount of time on operating cost. As switching costs increase, LCP outperforms other strategies because it minimizes unnecessary server load. Then we add prediction errors to simulate imperfect foresight. It tells us when the prediction is not correct, what will happen. Even with this error, LCP performance does drop significantly, highlighting its robustness to uncertainty. For PMR plots, we can observe that when workload has significant peaks, LCP is especially beneficial. This is easy to understand because if night doesn't use any nodes, we should just simply close it. So during off-peak hours, for example the nighttime, LCP can safely shut down servers, reducing cost without sacrificing the availability. We also test higher energy costs. This could come from relying more on the renewable resources, since they are more expensive. As the energy cost rises, LCP becomes even more valuable because it conserves power better than static strategies. Another alternative idea for LCP is valley filling, which is running some background task during the low load periods. On the MSR data, where the peaks and valleys are significant, running 40% background load during the valleys still leads to 15% cost reduction under LCP algorithm, shows that the LCP's efficiency and utility. Finally, we will impose server capacity limits, since in the real-world data centers, we usually have physical capacity limits. We test LCP under max server constraint, for example 80% of the servers. We compare it with LCP without limit and static provisioning. Even under this strict constraint, LCP still adapts to load conservatively and still achieves significant cost saving. For the extensions, based on current implementations, we can generalize the cost functions, making load versus power not linear. We can also do multiple layer switching, since in reality, the state is not only on state or off state. We can also have active states, sleep states, and so on. We can also do task migration and delay tolerance, resulting in a smarter scheduling. Integration with valley filling is also a very good idea. We could use LCP and valley filling together. It's like running a chain of coffee shops, each in a different city, and we need to coordinate the staff across them all. Same idea apply, but now it's a team of managers using LCP locally and coordinates them globally. To summarize, this paper suggests LCP algorithm, which is an efficient algorithm with no need to predict the future. And the LCP is very robust, even with inaccurate predictions, limited capacity, and high switching costs. It's more useful when workloads fluctuate, which is very common in model data centers. That's all for our presentation. Thank you.